Okay, hello and welcome. So today we'll be discussing the momentum and energy in special relativity. So let's write momentum and energy in special relativity. So as we have discussed in the last lecture that the relativistic Lagrangian LR was equal to minus mc square 1 minus u square by c square. This is what we have constructed out of the action, and that action was following the relativity principle that under any inertial frame, the action is basically invariant. So from there, we derived this Lagrangian and we fixed this factor based on the non-relativistic well-known Newtonian limit. Okay, so now we're just going to follow the definition for the conjugate momentum. So how do we define a conjugate momentum once given a Lagrangian? So let's say let us say we have this for a free particle. So this Lagrangian is for a free particle. We are not considering any interaction until now. So for this free particle, let us see what should be the momentum of a particle. So the conjugate momentum as defined is known as is basically given as del L over del let's say x dot j, right? So it is the conjugate moment. That's how we define the conjugate momentum, and we have seen in classical mechanics that this definition gives you like this is a generalized momentum. So it will give you the uh, angular momentum, right, under given particular generalized coordinates, right, in classical mechanics. But here we see that this Lagrangian is only a function of velocity, so it will not give you the generalized, the angular momentum. Rather, it will give you the linear momentum only. So that is pretty much visible here. And what do we do for energy? So energy would be simply q dot and okay. So let me just remove this q dot pq dot summation over all the components, right? And then Lagrangian, relativistic Lagrangian. So this should be our energy according to classical mechanics, and this should be our momentum, right? So this is what I'm assuming that you know already, because I'm assuming that you have undergone the course on classical mechanics 101, right? Okay, so let us just go ahead and just calculate these things. They should be very easy. So Pj should be del L over del x dot j, and let us write the Lagrangian in a more appealing form so that we should be able to differentiate it properly. So it should be minus u. So I'm basically u vector is the velocity of the particle, the free particle. So let us write it in terms of the component form. So it should be x dot j, or rather x dot I, summation over I from 1 to 3, right? 3 degree of freedom in the free space in the 3D world. So that is what it is. And we're not talking about right now the four momentum. This is just simply the three momentum. The normal 3D vector linear momentum we're talking about here, right? So Pj would be simply here uh, differentiation of this with respect to j, right? So let me just write up. So Lagrangian differentiation with respect to x dot j. So which will give us minus mc square upon 2 root 1 minus u square by c square, because this was just u square by c square, right? So it's rewritten in that form. And then we multiply and then differentiate. So this is just differentiation chain rule. So it would be minus 1 upon c square into summation over I, and then you get 2xi dot, and then you have something here, uh, dxi dot over dxj dot, right? Oh, sorry, this should be a partial derivative here. So this term survives only when I is equal to 0. I is equal to j. Only then this term survive. For I not equal to j, this is 0. So this is simply your canonical delta. So you can write Pj is equal to We can now simplify, like this 2 and 2 cancels, this c square cancels, so it would be plus, and this minus and minus will go to plus. It will be simply m upon under root 1 minus u square by c square. And let us see what we get here. So into this one here, this will go to delta ij, right? Summation over I x dot I and delta ij, right? So this summation here will survive only for I is equal to j. Only this term survives. All other terms are zero because of the presence of the chronicle delta, right? So this would be Pj is equals to m into x dot I, x dot j under root 1 minus u square by c square. What I think is that in my definition, when I defined the four velocity, it was a unitless quantity, so this c square should not be there, right? So everywhere this c square should be cancelled, I guess. And here, when I write u square, 1 minus u square, because that was. Oh, okay. Yeah, fine. My bad. This should be c square because that was not a 4. I was just confusing about this 4 momentum thing, 4 velocity thing. Okay. This is not a 4 velocity. I got confused myself. This is a 3 velocity only. Okay. This is a 3D vector. So no need. So this is not a dimensionless quantity. This has the dimensions of velocity itself. Okay. Cool. So we are good to go. So here Pj is mx dot j and divided by this quantity. Now this quantity we identify 1 upon under root 1 minus u square by c square is nothing but gamma. But again Lorentz factors come here. So Pj is basically m uj gamma in a more condensed form. So this uj is the component of the velocity. So basically I'm writing this as mux gamma, py is equal to muy gamma, and then pz is equal to muz gamma. Simple. So with the reference to the relativistic mechanics, non-relativistic mechanics, we well truly know that, sorry, we know that our momentum Pj in non-relativistic regime was equal to just muj and there was no gamma, right? So can we see that here? Can we see that whether this thing reduces to the our quantity of interest? Hmm? Because that is the actual test for everything we derive in relativity. Under the limit of v by c goes to 0, these things should be there, right? This should go to the non-relativistic regime. That is our greatest test. So Pj in relativity is muj upon under root 1 minus u square by c square, right? So now here if we just muj 1 minus u square by c square to the power minus half, and then we can write muj 1 plus u square by 2c square. Let us just retain one term, right? So here we are, and now you see that it should be muj plus some quantity muj u square by 2c square, right? And now we see that if we consider already this term survives, right? So this term is very less as compared to this term. So this can be approximately written as muj under the assumption that u by c is goes to 0. So this is very this term here, second term here is very, very small as compared to the first term. So only first term can be written approximately. So yes, indeed, we now see that Pj of relativistic NR, right? Relativistic momentum under the limit u by c goes to 0 thus corresponds to the Pj non-relativistic region. So we can convince ourselves that indeed we are good to go. There is, however, another way to check whether our momentum is correct, right? This gamma factor that we are multiplying or what we have derived, is it correct or not? So this could be a good exercise for you to do. I'm not going to do the detailed calculation. I'm just going to give you the idea. So what idea I have in mind is, let's say that you have a frame, right? And you have two particles here. Particle 1 goes with velocity v1, particle 2 goes with velocity v2, right? And then they collide, and then let's assume the elastic collision, and now you calculate, you know that the momentum should be conserved, right? We know that momentum should be conserved before collision and after collision, right? So after velocity, let us say you have V1A and V2A after, A for after, right? And now you see the same system with respect to a frame moving with velocity V along the x-axis. So there is a frame which is watching these balls, but it is itself moving with the velocity V with respect to an observer here, right? So now these velocities, you should have a way to basically to calculate these v1 and v2 with respect to this guy. So you need something called velocity transformation laws, right? You need to transform velocity into this frame, and then once you transform velocity, once you know the velocities, you can transform these velocities as well, right? And then you can use the two definitions of the momentum in this case. Use two definitions of momentum here and see, based on the transformation velocities, sorry, based on the relativistic velocity transformation, which definition is correct, or rather which definition of momentum is conserved. This is a good test to do, right? So I am just going to like, you should look up how do you transform velocities, right? It is very easy to drive. I will give you the idea for that as well. So the dx prime in the primed frame, which is moving with the v velocity, it is basically gamma dx minus v dt. This we know. And then dt prime also we know, it is gamma and minus v dx by c square plus dt, right? Now when you want to know ux prime, it is nothing but dx prime by dt prime. So you just divide these two quantities, take out dt, and you get ux minus v divided by 1 minus v ux by c square. So this is how the velocity transforms in relativity. Okay, in non-relativistic regime, ux prime would be ux and r. Non-relativity would be simply ux minus v. This we know already. But in relativity, there is a factor coming up here, and then again you can see that when v by c square is very, very less than 1, so this term doesn't matter. So it reduces, right? So this formula is also correct. Same you can do with uy prime, derive it using dy prime by dt prime, and uz prime dz prime by dt prime. Plug into these formulas where dy prime is dy only and dz prime is also equal to dz. So plug in, take out dt, and then derive ux, uy, uz. But you don't need to know the ux, uy, uz. I assume everything on the velocity is on the x-axis, so only this formula you need, right? And then you can transform here and then see which definition of momentum is going to be conserved. So you will find that the relativistic definition of MUJ gamma, this is what is conserved in both the frames and not the definition of MUJ. Hence, this is the correct definition of the momenta, right? Good test to do. Now, another thing, energy. Let's talk about energy now. Energy of the particle in relativity. So in classical mechanics, we know in non-relativistic classical mechanics, we know for a free particle, energy is simply equal to half mu square because energy is just equal to the kinetic energy of the particle. So nothing, nothing so fascinating about it. But let's see in relativity. So in relativity, because our Lagrangian is changed, naturally we expect our energy to be something different. So our relativistic Lagrangian was this one here, and our energy is given by basically Pj q dot j minus the relativistic Lagrangian. So we now know the Pj, or here I should again, I'm very habitual of using the q dot because that is how I learned in classical mechanics, but now I'm using xj, so let us stick with that. So Pj we have derived, it was just muj gamma, and there is a summation on j. Of course, you add up all the components, and then x dot j. But x dot j is again uj, so you just square it, right? Nothing great. Plus mc square, and again realize that this is just 1 upon gamma, right? So this thing here summed over all this, sum over all the components, you can write in vector mod form as this, right? Plus mc square by gamma. So this is what we get. And remember, gamma here is just 1 upon 1 minus u square by c square. This is our gamma, this quantity. Okay, let us go to the next page. So we have this as energy. Now it just remains to be simplified. We can simplify it, take out m, right? And you will get 1 gamma here, and then you will get c square, right? Plus gamma square u square. So it would be m by gamma c square plus u square 1 minus u square by c square. That is what is gamma. So energy is m by gamma c square minus u square when multiply here and plus u square, and again 1 minus u square by c square. Okay, so what do we get in the end? So basically it is m by gamma, and this quantity in the denominator, so this cancels, so it would be mc square, and this is nothing but gamma square, right? 1 upon 1 minus u square by c square is gamma square. So multiply that by gamma square, gamma gamma cancels. So now in the end we have a very special and famous formula, mc square gamma. So this mc square gamma is what is energy. So it looks to be very far away from the classical, I mean the non-relativistic regime. But let us see whether this is corresponds to the our non-relativistic regime under that limit. So relativistic energy ER is mc square under root 1 minus u square by c square. Right, and now again we apply the same trick, do the binomial expansion. So it would be minus 1 minus u square by c square to the power minus 1 by 2, and this would be mc square 1 plus u square by 2c square. So relativistic energy comes out to be mc square plus half m u square. So this one here looks a little different because here we are saying that the relativistic energy is something mc square. There is a quantity mc square here, and then you add up some kinetic energy half mu square, which we are very familiar with, and then you get the relativistic energy, right? But in the non-relativistic energy, it was simply half mu square. A free particle moving is having a half mu square, and when u is equals to 0, so you can see here that when u is equal to 0, when the particle is not moving at all, in relativity we have some energy at this point. We have a rest, this is called rest mass energy, but the non-relativistic energy is equal to 0. So non-relativistically, we don't have any energy, but here we do have energy. How do we explain this result? So here we have to the idea of Einstein was the particle that is still. So you have to think about the energy mass interconversion. So he said that the way you can think about it is like if you have a mass here, if you have a mass here, m that is sitting quietly, right? So due to this mass, this has some energy. Due to presence of the mass, this has some energy, right? And now if you break the it into two pieces, right? And then if some energy is released in the process, then it is not necessary that these masses of these two pieces add up and give this complete mass m. So basically, the thing is that this can be seen in the sense that mass is something not very fundamental, but energy is more fundamental than mass. And it is the law of conservation of energy that holds, and not the law of conservation of mass. In general, it does not hold. But under the assumption of very small velocities, you can prove that the mass of conservation, the law of conservation of energy actually equals to the mass, equal to the law of conservation of mass. But the main point here is if the particle is sitting quietly, then in relativity, for that particle, you have some energy. You cannot say that energy is zero. There is some energy even for a free particle, but there is no energy in the non-relativistic regime. Why? Because the way we infer, the way we interpret energy and mass, that is different in relativity and as compared to the non-relativistic result. So that is some new insight here, and you can read about it in the relativity books more.